So good morning, everyone. In the previous class, we were discussing about the magnetizing curve of any ferromagnetic material, and in that, we have seen that how the magnetization takes place. Okay, so what we did, we have considered one core made up of any ferromagnetic material. So this is a core, and then we wound coil insulated. Obviously, it is insulated from the core. Okay, there is no physical connection directly between the core and coil. Remember, and when it is connected with the source, and when the current to the coil is increased, let's say I have a variable source. When the current through the coil is increased, there will be a magnetic field set up in the core. Okay, there will be a magnetic field set up in the core. And I have also discussed that how, what is the reason that there will be a magnetic field set up in the core. Anybody remember the reason? That if I increase current through the coil, more flux will be set up in the core. What is the reason? Anybody remember? Yes, due to alignment of the domain, correct. So it is due to alignment of the domain of the material, and that is how we categorize the material. If domains are already aligned in the nature, inherent itself, then we call it as a permanent magnet. Where there is a already natural magnetic field present in the material. Second is the electromagnet. So in the electromagnet, the magnetic field is not inherent there. But if we externally apply force that we call as the magnetomotive force in the net. So if we externally apply the force, then the domains can be aligned and the efforts required, that is current circulated to the coil, and the proportionately what is the magnetic field set up in the core is nothing is the BH curve of any ferromagnetic material. Okay, so that is what is BH curve. And then we also have seen the hysteresis. What is hysteresis? So there is a slight difference between BH curve and hysteresis as discussed. Uh, we have seen here that H is the magnetic field intensity given as Ni by L. B is the flux density pi by A. So generally, suppose say for this coil and core which we have considered here, the number of turns are fixed, length of the magnetic circuit is fixed, so I is the only variable quantity. So I can say here it is I versus phi, because here the cross-sectional area is also constant. So it is either, if I say it is a BH curve or it is a phi versus I curve, is same thing. Okay. And we have seen that when we magnetize the core for the very first time, uh, here you can observe that as the current to this coil is increased, okay, that will give us the field intensity is equal to Ni by L. So current will, as the current to the coil is increased, flux will proportionately increase, and it will follow this, you know, nature. Where let us call this as the maximum flux density, or let's say, let me call it as a mean point voltage. So this is the point which uh, will be the maximum flux that can be set up in the core without any saturation. We will also discuss about the saturation region in this class. Okay. So let's say we have magnetized the core up to this point. So what we did, we actually increased current through the core here, and due to that, the flux in the core has increased, etc. So this happened because here the magnetomotive force Here the magnetomotive force MMF that we have increased, so the more and more domains that have aligned. in one line. So the magnetic flux lines have now increased. Now, what if we, uh, so let me call this as in this case, value of I and value of flux. Okay. So first here, when the current is zero, flux is zero, this is the point. Okay. Let me call it as a O, point O. From point O to point A, here the current is maximum to the coil tip and the flux is also maximum without any saturation. So that is point A on the curve. Okay. So this is called as the magnetizing curve. How the core material will be magnetized. That is the relation between the flux linkages here in the core versus the current through the coil. So this OA represents change in flux set up in core due to change in current through the coil. Okay. Now, so this is curve called as the magnetizing curve or BH. Or another name is also magnetizing curve. Okay, so OA is a BH curve or magnetizing curve. Now, hysteresis is slight different than this pipe because here we have magnetized the core with only flux set up in the one direction. This is due to this. This is it is acts as a north pole. This acts as the south pole. So flux lines direction are like this. Okay, and as we increase the current through the coil, the flux lines, more flux lines uh, will set up around the core. So this is part 1, part 2. Now what do? We gradually again make current to 0. So let me call it as a point B. Okay. So here the current to the coil is now made again 0, but flux is not 0 at this point. So there is some flux retained that we called as the residual flux. That is, once this force has been taken out, the magnetomotive force is made 0 because let's say Ni magnetomotive force here, MMF we have made 0, current through the coil is 0, but still few domains still remain aligned, and that gives the residual flux in core when the MMF is 0. Okay, and this property is known as the retentivity. This property is known as the retentivity. Okay, and OB is the residual flux. Now, if I want to make this flux 0, that means the domain which I have aligned in one line, even though after the force is taken out, now I want to make this residual flux 0. So what I need to do, I need to apply force into opposite direction. So what do we do here? We change the direction of current through the coil. Change direction of current through coil. Okay. So what we do now, we pass the current in the opposite direction. Let's say I equal to I dash. So then this point from B, it sits to point, let's say. So again, flux is 0. and that point on this curve is C. Okay. So what is OC? OC is known as the co-erosive force. Co-erosive force, that is the force required to apply in the opposite direction to make residual flux zero. Okay. And now if we continue, this is in the opposite direction. If we continue to pass current in the opposite direction by changing the battery terminal, flux will reach maximum in the opposite direction, and that will be the point B. Let's say. Same way, point A, likewise point A, now it is point B, so where the flux has already reached in the opposite direction, like this. Okay. So flux in the core is set up in the opposite direction. Now this acts as a north pole, this acts as a south pole, and here you can see the flux line. So again, if we pass the current to the coil in the opposite direction, that is we pass it till the maximum flux. So that is point B. Now again, I gradually make this current zero. So flux will not be zero, but it will be stored. There will be some stored magnetic flux, just like a point B. Here it will be point E. It will be stored in the opposite direction. And again, I want to make this flux stored zero. So I need to apply current in this direction S. So again, OS is the corresponding force required to apply to make this magnetic field zero. And if we continue this again, then it will set up the maximum flux. Now, see in AC applications, what will happen? I will show you. In AC applications, what will happen? Suppose we have a cord here, and there is a coil wound, which is in fact, this is applicable to all the machines. Okay, it is applicable to all the machines, transformer, induction motor, generator, everywhere. And suppose this is the machine winding. Okay, and this is the machine core over which the winding is wound. Now this is an AC source. So what will happen here? It is alternating in nature, I time t. So continuously the magnitude of current will change, as well as the direction will also change with each half cycle. So what will happen here? As the current increases here, at this point, the flux set up in the core will be peaked. Okay. So during this part, I'm saying during this part, okay, what will happen? This thing will happen. Then, as the current has reached at the peak, flux in the core here is the maximum, this part. Okay. Let me specify during this part. Okay. Then, what will happen? The magnitude of current will decrease. So, in this part, this will happen here. Then, the flux will be set up in the opposite direction here. I'm talking about the when the it is connected in the AC circuit. So this will happen, and then finally during this part, this will happen. So in AC circuit, what is happening? In AC circuit, when winding connected with a AC source here, the direct magnitude and direction of current is continuously changing. Okay, and so the flux setup in the core will continuously change, starting from 0 to max to again 0 to again max in the negative direction, opposite direction, and then again 0. And this cycle will keep on repeating with each completed cycle. Okay, and this is called as the hysteresis. BH curve is only the magnetizing curve. Let me show you. This is BH curve. This part is BH curve. Okay, what BH curve represents? This part is BH curve. BH curve represents the magnetizing of core. It represents how the core will be magnetized. Whereas, what does hysteresis represent? Hysteresis represents that how the flux will be set up when core material is subjected to reversal of magnetic field. Okay, so they are different. Hysteresis is about when the core material is subjected to continuously reversal of the magnetic field, then how it will behave. And BH curve is one where it will represent that how the core material can be magnetized in a cycle. Okay. Now, what will happen when the core is subjected to reversal of magnetic field? You will require some energy uh, to continuously change the position of domain, because as now in AC application, continuously the magnitude of flux and the direction of flux will reverse over a period of interval of half cycle. So magnitude is continuously changing. Let's say from 0 to peak, peak to 0, then in the reverse direction 0 to peak, peak to 0. So the domains will continuously change their position, and then you require to overcome this, to you require some energy to do this work, and that is what we call as the energy lost or dissipated in form of heat, while the domains will change their direction continuously, and that is called as the area under this hysteresis curve defined, and that is called as the hysteresis law. So this area under the curve represents hysteresis. This is the energy which will be converted into heat energy due to continuous change of the position of the dipole domain. Okay, dipoles in the material. So am I clear? What is the difference between hysteresis and BH curve? BH curve represents the magnetizing of any core. That if you want to set up a specific value of flux in the core, what is the magnetizing force you need to apply? So that is the magnetizing force applied versus the flux setup in the core. That is BH curve. However, if the magnetic material is subjected to continuously change in the magnetic flux, in the magnitude as well as the direction, then some of the energy will be dissipated, will be converted into heat energy due to continuous change in the dipole position, and that is what represents the system. Okay, so am I clear with this? The difference between BH curve and a hysteresis curve. Okay, now let me show you this. this is what we have discussed. This is uh, magnetizing force plus density, magnetic flux when it is magnetized for the very first time, and then uh, imperativity property, residual flux, coercivity, coercive force, we can say, force required in negative direction to make the residual flux zero, and then this is the change in the direction. Now you can visualize this here. Whatever we have discussed is shown. The this is the first initial movement when the core is we are about to excite the core. Okay, this is the cross section of the core. It's a representation of the domain in it. This one. Okay, so it is showing the cross sectional area of the core with the position of the domain like this. This one here. You can see. And when the core is excited, the core is wound around it, and when the current is passed, so initially this part is the first part where the material follows non-linear magnetizing curve when the magnetizing from 0 to field here. So this is the point you can see here. Material is magnetized, and you can see here the position of the domains. Okay, here it is random. Every domains are not aligned in one line. There is no magnetic field at this point. But as we have applied, as we have increased current through this, as we have applied the magnetic field intensity, we have increased here the magnetomotive force. Then the domains will, some of the domains will keep on aligning themselves, and that is why the flux will increase around the core. And you can see here the alignment of the domain in one line. So here we have reached to the saturation region. Okay, I'll also explain the saturation. We will see in detail. Don't worry. Now, then when the driving field drops to zero, the ferromagnetic material retain the considerable amount of magnetization. This is one of the important property for the poles. Remember, when we discuss why we are discussing this, because this is very important. In fact, when we discuss about the DC generator and DC motor machine, because in self-excited machines, this will be one of the very important properties that is required to see. And then you can see when it is made to zero, again the domains here and here are same. That means the domains are back to their original position when the flux is not there. And then we apply the magnetic field in the driving magnetic field, that is magnetomotive force, in the opposite direction. You can see the position of the domains are exactly opposite than this, and so on. Okay. This is, you can see that what is hysteresis loop shows. It shows the history-dependent nature of magnetization of a ferromagnetic material. Okay, once the material has been driven to saturation, the magnetic field can then be dropped to zero, and the magnetic material will retain most of its magnetization. It remembers its history. Okay, now let me explain what is a saturation region. Okay, is this clear? Is this part clear? Magnetizing curve or BH curve and the hysteresis curve. Anybody has any doubt?
Me आता little hard.
Yes, Abhijit? Any doubt, anyone? Okay. Now, so let us explain. See the linear and non-linear region on the BH curve. Okay. Now, let me go back to the slide and let me explain you the linear and non-linear region. Okay. Okay. Let me say it here only. Okay. Now, if you see the BH curve here, which represents the magnetizing of any core, and the nature is like this. So this is the initial non-linear magnetization. Here you can see where it has total three different regions. We can see one point is here, which I will call as the A point. The other is K point, and this A point and K point are nothing. They are the ankle point and knee point of the BH curve or the magnetizing curve. Okay, this is the magnetizing curve. Now, see, in this region from O to A is non-linear. This is a very small region on this characteristic. Okay, which is very small. In fact, if we obtain it in the laboratory, you may not be able to even visualize this region. A to K region is the linear region. I'll explain what is the meaning of linear and non-linear region on the BH curve. And from K onwards, again it is non-linear region. Okay, again it is non-linear region. So I'll show you what is the meaning. I'll explain what is the meaning of linear and non-linear region. Now, for that, here you can see that if we increase the h in this region, we will not increase proportionately. That means if there is a core and there is a coil which I have wound here. Okay. So during this region, during this magnetization part, if I increase the MMF, the magnetomotive force here, field intensity, the flux setup in the core will not be proportional to current, will not follow this region. So that is why it is called as the non-linear, because the proportionality between if we increase the current here, and due to that the flux setup in the core, this part, will not be the in proportionate manner, and that is why this region is a non-linear region. Okay. Then comes the region A to K, which is most important part for any machine. All the machines, if we talk about the generator, motor, transformer, any machine, the core is generally designed to operate in this region, A to K, linear region. Why linear region? Because in this region, if we increase I, the domains will align proportionately and with the field intensity, magnetic field intensity, and flux will set up will increase proportionately. So that is why it is called as a linear region. All the machines are designed to operate in this region. It is a linear region. Remember. Okay. And K onwards is a non-linear region, is also called as the saturation region. I will explain this in detail. What is a saturation region? So, what we are doing here, we are increasing the current through the coil. So, magneto-motive force we are increasing here. And that is why this domains will keep on aligning. As we increase the current, let's say right now, for example, if this is the flux setup in the core, okay, and due to that, this is the current, and due to this current through the coil here, this is the flux setup in the core, for example. Now, if I increase the current here, let's say this I2, the flux setup will also increase to phi 2 level. If I still further increase current through this core here, let's say I3, then the flux setup in the core is phi 2. Okay, we are talking about the flux setup in the core here. What do you observe in this region? As I increase the current, flux increases proportionately, or it is not increasing proportionately. What do you see? Does the flux follow the linear relation with the current? Yes or no? Yes, it is proportionately increasing. So that is why the region is called as the linear region. Basically. Okay. Now what will happen? Let me show you. Is now we keep on increasing this. Okay, we keep on increasing this current. Now there is a limit here that comes to any point. Okay, so at any point, what will happen? We have reached to the mean point. Okay, and let's say we have set up this much flux, and for that, this is the magnetizing current required to set up this magnetic flux phi n. Okay, now this is the point where we have reached if we think of the alignment of the domain. Now, most of domains they have aligned themselves in the one direction. Now, very few domains that are left in the core. It depends upon material, okay, in the core. So, now if you want to increase the flux in the core, if you further want to increase the flux in the core, you need to align more domains in the line. Now, this domain will require some very large force, and that is if you want to change flux by 10% after knee point, how we define knee point? Okay, this is the definition of knee point on BH curve or on a magnetizing curve. If somebody asks you what do you mean by a knee point of any magnetizing curve or a BH curve, then knee point is the point where afterwards, if you want to change flux by 10%, the magnetizing current required to change this 10% flux is 50%. See how huge magnetizing current you require to set up the additional extra magnetic field after this point. Until this point, what was happening? If you increase magnetizing current by 10%, flux will also increase by 10%. If you increase by 5%, it will increase by 5%. Okay, if you increase by let's say 1%, then flux will also increase by 1%. It was a linear relation between the flux set up in the core versus the current through the coil up to point K. After point K, which is a new point on the magnetizing curve, if you want to increase the flux by 10%, then the magnetizing current required is 50%. And still, if you continue this, If you continue this point, let's say, then you can see the region becomes flatter here, and then it will require a large magnetizing current to establish a very small flux in the core. That means your material has saturated now. Now, any force, additional force will not make any much difference in the flux in the core. The core is saturated. Saturated means now further, even if you provide any additional amount of force from here, magnetomotive force, if you provide magnetizing current, still the flux will not increase by significant value. And this is a very dangerous situation for any core material because it has driven into saturation and the magnetic field can be dropped to zero. So this material can lose its property after this and again cannot be used as a core material if this happens. The material property will change and then you cannot use the same material again. Okay, let me show you what will happen. So here, suppose here we have, I'll explain you what will happen if the core saturates. Okay, what is the problem? We should not operate core into saturation region. Okay, so this is, let's say, H, this is P, and then I have taken one core material of any machine. Let's say this is a transformer core, and then this is a winding wound of the core. And for example, okay, let me take DC source simply. Sorry, H P core. This is the magnetizing curve of this core material. Let's say any cast steel, cast iron. Okay, and what we are doing, we are increasing current to the coil, and let us assume that coil has a sufficient capacity to carry the current. So we increase the current, flux will increase in the core like this. If we increase further current, flux will further increase and so on. And by this time, we have reached to the middle point at this point. Okay. Now further I increase the current, then flux will not increase proportionately and the nature will be like this. Okay. So now you see here what will happen. Suppose I want to change flux by small percent like this. You see the difference. How much magnetic field intensity is required to set up only this flux, only this small. See the difference that is you require in the magnetizing current. To set up this much change in the flux. Okay, and this is what is called as the saturation of the core. Now we continue to operate. Let's say we have operated core with this flux density. Okay, we have not taken appropriate care and the core has been operated in this saturation core. What is generally it should be operated in this region, which is a linear region. But anyhow, due to any reason, you will also study this, that what are the reasons that will saturate the core of a machine. But it is very early to discuss right now. This will be discussed in the subject later on in the semester. Okay. So then suppose I have a transformer core which I have operated in the saturation region. Now what will happen? The core material due to this saturation, core material has lost its original property And when I remove the magnetization from here, the domains will be completely different in a different process. So next time, if I magnetize the core, it will look like this. If I magnetize next time same core, it will be like this, or maybe like this. So the material will lose its property, and the core may behave in a very different manner each time when you magnetize the same core again. If you do not operate in the saturation region, it will always follow. If you operate at the core in the linear region, it will always follow this graph. It will always follow this graph, this BH curve or this magnetizing curve. If not saturated, but if it is saturated, it may happen that every time when you excite the core, the magnetization can be completely different. Now, can you use the same material again in the core? If this happens, can you use the same material again? My question is, where you don't know that how the magnetization will take place. Every time the magnetizing of the core may be different, which is not as per the material property. So my question is, can you use the same material now as a core in any machine? Yes or no? If the material behaves differently every time when you, as the core behaves differently when you excite the core every time. Do you understand my question? Why this happened? Because now the domains which we have seen here, uh, the okay here, when we take the magnetization back, if it is operated in the saturation region somewhere here, then the domains will not remain same. This domain you can see will completely different, and the material has lost its magnetizing property. Okay, so now is this material is of any use for us? Can we use this material again? Yes or no? If material does not behave in the same manner, the next time if it is saturated, it may magnetize like this. Second time it may magnetize like this. Third time it may magnetize. We don't know. It is a stochastic behavior. Stochastic behavior means when you excite the core, its behavior will be different every time. Okay, so then the core cannot be used. If it is, and we need to replace the core of the machine. So this is a non-linear region. This is a non-linear region, and generally the machines during operation are advised not to driven to the saturation region. So we are talking about core, okay? This all the thing is about the core of the machine, because BH curve is the curve of any core which is a ferromagnetic material in fact. Okay. So am I clear with the linear and non-linear region on the of the BH curve or magnetizing curve? Okay. Now I'll one more point I'll discuss. One more point I'll discuss here. Okay. One minute. Okay. Now suppose wait a minute. Okay. I have a material one. Okay, and I have a material two. I have two different materials. I'm not naming them right now. I have used as a core material. Okay. Now let me represent it with a different color. Material 2. Okay. So material 1 has a magnetizing characteristic like this, or a hysteresis characteristic like this. This is material 1. Okay, hysteresis. And material 2 has a hysteresis like this. Okay. Am I clear? What I want to convey, that I have two materials with two different hysteresis loops. Okay. Now, anyone from your anyone from you, can you tell me the relative advantages and disadvantages of material 1 and material 2? Looking at the hysteresis loop, you can unmute yourself, and if you can tell me, what do you understand from this discussion? Let me give you hint that on what point you can discuss. First, amount of residual flux, retentivity. Second, hysteresis loss. Sorry, 1 minute. Second is hysteresis loss. It is area under curve. Okay. And third, the flux density. It is how much flux is set up versus the field strength H for the same current. These are the 3 points. If you observe from this curve, and if you can tell me that what is your observation about material 1 and material 2 in this regard. Anyone? You can unmute and you can tell me. Yes, anyone? Observe the characteristics. Vivek, unmute yourself, please. Vivek. Okay, Deepu, unmute yourself. Yes, Deepu. What
Yes,
do you
sir.
see? What do you see here? What is the difference?
Yes,
See, Deepu Arbas Sahil, I have given this instruction number of times that you write down your roll number first, then your name. Even after 3 or 4 lectures, you are doing same thing. Sahil, Deepu Arbas, just look at the uh, just look at the name of other students. You don't understand it every time. Vivek, you too also. Why I need to give same instruction every time in every class? Arbas, Deepu, Sohil, Vivek, every time I am giving same instruction number of times in the same session. Then you will ask that my attendance is missed. Yes, anyone? Gaurav, Samir, Prem, anyone? If you can answer this quickly. You unmute. Please unmute and speak. No, don't worry. Gaurav. Yes, Gaurav, you can unmute. And okay, no problem. So you have written it in the chat box. Okay, correct. Your answer is absolutely correct. All three answers are absolutely correct. Anyone else? Anyone else? Okay, so let me compare this three parameters. Gaurav has correctly addressed all these things. Residual flux. So in material one, you can see when it is magnetized, let's say for the first time, and when the magnetic field intensity is brought back to zero, you can see this is the residual flux for material one. This is the magnetic flux setup in the core that it will retain. Okay, and for material two, here you can see the magnetic flux setup in the core is this. So which material will store more flux when the magnetic field strength is again zero? When you reduce current to zero, again, which material will store more flux in the core? One or two?
One, sir.
Correct. So flux one will, the material one. So material one has better retentivity. Okay. So if I am designing a machine where I require more flux to be stored when the current through the coil is zero, material one is the better option for me. Okay. Don't conclude right now anything. This is just one property that we can consider, that if I require uh, there is a requirement of the machine that there must be some residual flux stored in the core, then this better retentivity is the property which we should look for. So definitely the material one has the better retentivity. Okay, what about hysteresis loss? Which material will have more hysteresis loss? Where the input energy given will be converted into heat energy in which material? Material 1 or what? Material 2, area under curve?
Material one.
Material 1 have higher loss?
Higher, sir.
Yes, so this has a low hysteresis loss. See, all these things are very important. Why we are discussing that once we'll start the machines, all these things I'll directly say that this is the stresses loss of the material, or this is the magnetizing curve, or let's say when we will draw the characteristic, when we obtain characteristic in the laboratory, all these concepts we need to recall. That is why we are discussing this. So it has a low hysteresis loss. Okay, this one it has a higher hysteresis loss. Okay, for the same current, which material has more capacity to set up the flux? Let's say if I take this material, what do you think? This is the flux setup in the core with this magnetizing current in 1, and this is the flux setup in the magnetizing 2. Okay, so if I take same cross-sectional area of material 1 and material 2, which one has higher flux density, material 1 or material 2? For the same cross-sectional area I am talking. Which material has higher flux density, capacity to set up the magnetic flux with the same magnetizing current? 1 or 2? Higher. For the same current, if let me just again draw it. Okay. Now again I'm drawing this, so understand clearly. Suppose both the material 1 and material 2 have the same cross sectional area. Okay, same cross sectional area both this material. So B is equals to phi by A. This area of material 1 and material 2 is same. Now the flux at this current I, the flux set up by material 2 is this. Okay, this is the value of flux it will set up, and the flux set up by material 1 is this, and material 2 this. Now what do you think? With the same magnetomotive force, the material 1 has higher flux density. Okay. Now, so here it has a lower retentivity comparison, and here it has a less flux density for same cross sectional area. Now, the advantage of material 1 is that it has a better retentivity and higher flux density. On the contrary, it has a higher hysteresis loss, whereas material 2 has a lesser retentivity property, and also the flux density is lower, but it has a less hysteresis. So, what generally we do? Okay, I think time is over. So what we do, we can make this two material combine and prepare a composite material. Which has better retentivity, lower hysteresis loss, and better flux density. Okay, so more on this we'll discuss in the next class. I think time is over, so we'll continue. Okay. All of you are requested to write down your enrollment number quickly, and then you can leave the class. Okay. Thank you, everyone. Whose class is next? Next lecture is okay. No.